Hello. In this video, I'm going to explain problem 4 from the 2014 F equals ma contest. We are told to find the maximum number of particles that would satisfy the maximum numbers n1, n2, n3, all referring to the number of particles that a single particle explodes into, such that certain conditions would be guaranteed to be satisfied. So the first condition reads, if a particle at rest explodes into n1 or fewer particles with known masses, and the total kinetic energy of the new particles is known, then the kinetic energy of each of the new particles is completely determined. Well, of course, since we have a particle at rest exploding, that means that the total momentum is 0, and this is going to be true throughout this problem. Now, let's look at that first case. If the kinetic energy is, suppose that we have two particles, let's say M1, M2, then let's say, so the center of mass would just be the site of the explosion, and then what we will have is that they'll move with some speeds v1 and v2, and we know that they're vectors, and we know that m1 v1 vector plus m2 v2 vector is the 0 vector. But that means that v2 is just negative m1 over m2 times v1. So v2 is just a scalar multiple of v1, meaning that v2 is parallel to v1. And that actually means that the particles must move in a line, or the particles' trajectories, I should say, must lie on a line. Now, how about three particles? Well, we would have m1 v1 plus m2 v2 plus m3 v3 equals 0, the 0 vector, and so v3 would be negative m1 over m3 v1 minus m2 over m3 v2. And so what does this mean? Well, it means that v3 is a linear combination of v1 and v2. So if I have v1 and I have v2, then these two vectors span some plane, or that is, all the linear combination of these vectors form a plane, and v3 must lie in that plane. And so it follows that the particle's trajectories must lie on a plane, but not necessarily a line. Now, how can we show for sure that it's not necessarily a line? Well, the simple way would be to just have three particles all going off completely symmetrically. Let's say if they're all of the same mass, and then they all go at the same speed at 120-degree angles, then this will be, trajectories contained in a plane but not a line. So ultimately, we actually finished the second one first, and we saw that if a particle at rest explodes into two particles, the velocity of the particle has to lie on a line, but if they lie on a plane, or if the particle at rest explodes into three particles, then they do not need to lie on a line, meaning that n2 must be 2. Now, we've already made progress on answering the third scenario, because we just showed that if it's 3 or fewer particles, they must lie on a plane. But how about 4 particles? Well, we can do the same thing as a symmetrical configuration, but we can instead have the particles move in the directions of a regular tetrahedron from the center. So if we have a tetrahedron, which is basically a solid with 4 triangular faces, and if it's a regular tetrahedron, then all of the sides are the same and all of the faces are equilateral triangle. And from a center point, which this is like inside the tetrahedron, we can have the particles move toward the vertices like this, and it'll be completely symmetric. So if they all have the same mass, then the total momentum is 0. So this is an allowed explosion, but you can see that this motion does not lie in a plane. And thus, for 4 particles, the velocities do not need to lie in a plane. And thus, we have n3 equals 3. And so now, how about n1? So we need to think about kinetic energy. And one thing we can see is that if we have 2 particles, let's say we have so K, M1, and M2 are known. And we also know that the ratio V2 over V1, so this is absolute value, will be M1 over M2, which means that really, if I write 1/2 M1 V1 squared plus 1/2 M2 V2 squared equals K, then substituting in this formula, what we will get is M1 V1 squared plus M1 V1 squared times M1 over M2, because V2 will equal V1 or times M1, or it'll be V2 is negative V1 times M1 over M2, and so V2 squared will be V1 squared times M1 squared over M2 squared. And then we will get 2K on this side. And so what we get is M1 V1 squared 1 plus M1 over M2 equals K, and that means that we can solve for V1, and of course then we can solve for V2, which means that if we have 2 particles, then the velocities are all known, assuming that we know the kinetic energy and the 2 masses. So how about 3 particles? Well, now, you might be able to suspect that we can find a counterexample. And you can see that this derivation sort of gives you an intuition that you were basically able to bring it down to sort of one free parameter and then solve for that. However, you can sort of probably be able to tell that this may no longer be the case, and the easiest way to show that is to just produce a counterexample. And how can we do that? Well, all we have to do is just to produce 2 possible scenarios in which momentum is conserved, but the particles have different velocity ratios. And so that's the key here, because there's only one mass ratio, m1 to m2, then the velocity ratios are known due to conservation of momentum, and then that automatically tells you their velocities if you know the kinetic energy. But here, because there are 2 possible free ratios, m1 over m2 and m2 over m3, and just the total momentum has to be 0, you no longer have that kind of freedom. And so one thing we could do is that, let's say we have 3 particles, all of mass m, then we could draw 2 different scenarios, one in which they move something like this. So we could have V, V, and V. and so they're all mass m. And again, this is a 120-degree angle. Whereas in the other, where we can draw another case, pretty much anything will work, but for example, I could draw 2v2 and now have both of these particles moving down in the same direction with, you know, v2 and v2. And so now what you can see is that even if the kinetic energy is determined and the masses are all determined, which they are, then the velocities are not determined, because we could have, for example, them in this 1-to-1-to-1 ratio, but we could also have them in this 1-to-1-to-2 ratio. And so that means that it's not determined. And so since we could determine the kinetic energy of, and remember, determining the velocities ultimately, or determining the speeds of the new particles does mean determining the kinetic energy. So since we could, let me be clear about this, this is velocity, or speed ratio. So that's also 1-to-1 kinetic energy ratio, and this is speed ratio. And so it would actually be 1-to-1-to-4 kinetic energy ratio. And so, since you can determine it for 2 particles but not for 3, we have n1 equals 2 as well. And so, thus, our answer right here, n1 equals 2, n2 equals 2, n3 equals 3, is the correct answer. All right, and that concludes this problem. Thank you for watching.